We will try to explain what we mean by a metric space. So suppose that X is a set and we wish to start measuring distances between the members, the elements of X. Then what we need is a function that takes as inputs any two elements of X and assigns to them their distance. So a function D defined on X times X with values in R is called a metric if it satisfies four properties. The first property is that it's non-negative. So the distance between any two elements of X is greater than or equal to 0. The second one is that if you have different elements of X, then the distance between them is positive. Indeed, if it was 0, it would be as if we wanted to identify two distinct things, and that would be a little problematic. So D AB is equal to 0 implies that A is equal to B. And we could say, of course, and the other way around. So the third property is that the distance from A to B is equal to the distance from B to A. As we say, distance is symmetric. Again, this is something that, according to our experience, it's only quite natural. And the last property is that the distance from A to B is less than or equal to the distance from A to C plus the distance from C to B for A, B, C in X. We usually call this the triangle inequality because if we sketch a triangle with vertices A, B, and C, then we see that this reflects the fact that the distance from A to B or one side of the triangle should be less than or equal to the sum of the other two sides of the triangle. Of course, even in the simple case of a Euclidean space, the equality can hold true if, for example, you had the line segment and C was between A and B. So a function is called a metric if it satisfies these properties. The space, the set X equipped with the metric T is called a metric space. So sometimes what we actually say is that the pair X, T is a metric space. Occasionally, we will have a set that we wish to equip it with more than one matrix. And in that case, we should make it quite explicit which metric we consider at any given moment. Now, one can give many different examples of metrics. So, for example, if we are in R2, then the metric from a point A1, B1 to A2, B2 can be defined in a variety of ways. So the usual Euclidean metric, as we say, would assign to this pair of points the length of the segment connecting them. So this will be A1 minus A2 squared plus B1 minus B2 squared. We have another interesting metric, the cap drive metric. So here, what we do is, if we want to go from this point to that point, we go like this, as if we were in a city that had blocks, and we had to proceed in such a way. That's why this is called the cap drive metric. And of course, there are many different metrics that one could mention. And it would be a good idea to finish with one metric that seems rather trivial, but it's occasionally interesting, and it can be defined on any set. It's called the discrete metric, or to be more precise, a discrete metric, because there's more than one ways to define a discrete metric. And this is the metric that assigns to a pair of elements of our set the number 1 if A is different from B, and 0 if A is equal to B. Again, the proper way to describe this is as a discrete metric, because there are other metrics that pretty much can do something can have a very similar effect. So that's what we mean by a metric space. Thanks for watching.